Hi, my name is Erik and I'm a PhD student at the TU Berlin. I'm going to talk about privacy for Bitswap requests. Bitswap is the default data exchange protocol in IPFS. And if you think about Bitswap, you might know how it works, but now you might think, are there any privacy leakages? Let's just take a look. Now here you can see the Bitswap process. We have at the beginning an initial discovery phase, answer, file transfer, and if we can't find the specific CID in our neighborhood, we have the DHT requests. The problem here is all those somehow leak information. On the one hand, what one person is interested in, on the other hand, what another person stores. Here for our presentation, we use client as the one that is requesting information and server for all other peers. Now, what we want is to obfuscate the first part, the 1/2 part. We want to obfuscate the item of interest, and this should be done with a low latency approach. It should induce a low computational cost on the server side and ideally has a low overhead on the client side. Now, if you think about it, what is the simplest approach that you can do to gain the information what a server is storing without revealing your item of interest? Well, it is to simply ask him for everything he's storing. This can potentially have a large overhead. Still, if you improve this idea, which we do, it should be still manageable. Our improvements are using probabilistic data structured and private set intersection. Now, probabilistic data structures are a structure to approximate membership in large data sets. The most commonly known example are Bloom filter. I'm assuming Bloom filters are known. Here in the graph, you can see a rough outline how they work. I'm referring to the papers and the footnotes if you're interested or need to refresh your knowledge again. Now, how would probabilistic Bitswap look like? Well, you have the 1/2 request, and instead of requesting your item of interest, you request the probabilistic data structure. Receive it, look up your item in the probabilistic data structure, and then if it's a match, you request the block from the server. Then you receive the block, and you're happy. Of course, there is this slight problem. It's probabilistic Bitswap. These probabilistic data structures, while they have no false negatives, they can have false positives. These false positives have the advantage for the server that they provide plausible deniability. However, this is the downside of this approach. If it is a false positive, the item of interest is revealed without getting the block. Here you can also see follow-up requests don't need this probabilistic data structure, need to request this probabilistic data structure again, assuming, of course, the server set hasn't changed in between. Now, the next approach uses private set intersection. Private set intersection is used to privately compute the intersection of two sets. And those two sets are, in our case, on the one hand, the client wants, so what the client is interested in, and on the other hand, the stored CIDs by the server. This private set intersection can leak the set sizes of both parties, so the number of CIDs the client is interested in and the number of blocks the server stores. The next approach, which I'm showing, uses elliptic curve Diffie-Hellman PSI. So if you know a bit about Diffie-Hellman, you might see something which looks awfully familiar. Yeah, so ECDH PSI Bitswap. The client requests again, as for the probabilistic Bitswap request, U is here the storage information of the server. However, he also requests V. V is somehow transformed multi-hash of the client's interest. So it's not the pure CID, but it's magically transformed. The magic here is basically hashing the multi-hash to the elliptic curve and then multiplying it with a random number of the client's choosing. The server answers with all his stored CIDs. In this case, they are also transformed, of course, and he also transforms the received V by also multiplying it with his own random number and then sends them back. The client then can do the whole PSI matching, again applying some math to the received value, seeing if it's in the set, and then if it is in the set, okay, he knows I can request that block, receives the block, and the whole exchange is done. Also here, again, the requesting a view is a one-time overhead as long as the set of the server doesn't change and can be skimmed on follow-up requests. Now, we can already think about one improvement if you think about the probabilistic Bitswap, and by making this a probabilistic ECDH PSI Bitswap. This is just changing U to a probabilistic data structure. If we take a Bloom filter, what we would do here is not use a multi-hash to determine the bit position, and instead we would use the transformed. So we would use the elliptic curve point. So hash to curve and then multi-hash, hash to curve, getting a point, multiplying this point with the random number, and then we will build a hash out of it to determine the bit position. Okay, now let's assess this approach. PSI protects the client privacy. We don't request the CID, we request an elliptic curve point, which can be from receiving this point, the server cannot recalculate the CID. So this protects the client's interest. We can integrate this in Bitswap within reasonable overhead. We have a one-time overhead of the calculation of U and the server side and transferring, of course. The advantage of this approach is the server has to calculate this only once for all his neighbors. Still, this is a one-time overhead on the server side. If we only look at transferred byte and excludes this one-time overhead, we have almost no additional transfer. We have want-have messages which the client sends to the server, and we receive a don't have. So no additional messages, and the data that is sent is basically an elliptic curve point. If we use Ristretto 255 curve, then the compressed point size is 32 bytes. What are the next steps? Of course, an intensive evaluation of the approach. So while we know, okay, the transferred bytes aren't that huge or almost non-existent, it still could induce some computational overhead. I can already spoil a bit. If we think about Ristretto 255 curve again, we have an encryption time of around a millisecond for 10 CIDs, and 10 multi-hashes to be more precise. Still, there's some additional accounting to be done and management of the messages which to send and so on. So this needs to be further evaluated. Another problem are large sets, more than 10,000 or maybe even more than thousands. The whole range is not yet known by us. One simple extension which could be done is reducing the size of U. This is by just leaking a few bits of information, we could reduce the potentially large U by simply saying, okay, we only want you to include in this Bloom filter CIDs using SHA-256 for the multi-hash, and maybe even leaking a few bytes of the digest. And if those conditions aren't fulfilled, you don't have to include them in the Bloom filter. And this would reduce U, which is the biggest overhead. We assume here, of course, that it's unlikely that the client requests thousands of CIDs at once. In the future, we also want to think about how we can extend this to include the transfer of the data associated with the element. So in this case, not only finding out if the server stores it, but also privately retrieve the block. There are some PSI approaches which allow this transfer. However, we need to see if they're suitable and if the overhead is then too large. Another part we want to take a look at is if this can be extended to also include DHT requests, or in general, if PSI is suitable for DHT requests. Before we come to the end of this talk, let me give you a small demo or example for Bloom filter requests. Here we have just a small table. You can see this is from the client's perspective. Direction means out, here means sending data, in means receiving data. View is internally, what Bitswap is doing internally, and wire is what the server would receive. Yeah, and here we can see, okay, internally, the client wants a specific CID. What he sends to the server is only a small dummy CID. So the server knows, okay, this client wants the Bloom filter. What he receives is the Bloom filter. And after a lookup, in this case, the server stored it. You can, okay, send the CID he is interested in. So we have here this internal have. So the lookup was successful. And then we can send one block, and after receiving the block, we can send the one block cancel. Now, for PSI, this looks a little bit different. In this example, we already exchanged the Bloom filter. We received it earlier. However, what we can see here is internally, this is a CID the client is interested in. And what he sends to the server is this CID. They're completely indistinguishable from each other. And the only thing that changes here is the digest, and in this case also the multi-hash code. If you wait a little bit, I show you this a little bit more in detail. And the important part here is also the don't have answer is also different from the send won't have. Internally, again, after executing the PSI protocol, you can then determine, okay, is this have or is this a don't have? It's a have, okay, one block, one block cancel. Now here, the three CIDs are in a bit more detailed. You can see here the version, multi-codec, multi-hash code, multi-hash length, and the digest. And if you compare the internal want and the send want, you can see here the digest changed and the multi-hash code changed. The multi-hash code is used by us simply for matching purposes. So if you look further, the received don't have, again, we have another digest, but we have the same multi-hash code. So to match this received don't have to the want, we need some kind of identifier. and we misused the multi-hash code for this identifier, and this is why this multi-hash code is different from the multi-hash codes of the original one. The important part is the digest. Here is the digest really the hash from the block. Here, this digest is an elliptic curve point in both cases. So also the received don't have this is an elliptic curve point. However, it's another one compared to this one. Yes. With that, thank you very much for your attention and have a nice day.